Believe it or not, there is something of an actual logic to our curricula here. And the plan today is to build on some of the modeling aspects we did yesterday and some of the intervention aspects we did before, and move to sort of the in silico sort of model truly from the ground up. So we had, network model-based simulations that Carter presented yesterday, and Scott and David also presented some of those with Sienna or REMS. And when those are fundamentally, sort of data grounded. And what I'm going to talk about today, I have the wrong slide up. What I'm going to talk about today are simulations where you know very little about the actual real world, and you're making things up whole cloth. So this is my joke is this is when this is the one time in your career that it's good to make up data. You just need to do it in a systematic way and be honest about it. And so, but the plan is to talk through a bit of what simulation and agent-based models can do for you, how they work, how you set them up, and then go through a couple of detailed examples that are currently in progress. Just as a way to sort of show you the scars, warts, and all, so that you can see sort of the way these things kind of get developed. From a program standpoint today, we will end around noon or so, and let me just double check here. Yeah, so the last session we're scheduled to go through till 1 o'clock, but we have a bunch of time essentially there, about an hour for Q&A, which is really just designed to be an open set. After I get done, we'll talk with Sam Jennis is going to speak on EPI model, which is a disease diffusion specific model that integrates ERGM with the kind of agent-based models I'm going to talk about. And then hopefully Peter Cho and Jesse Lin, Peter's right there, there we are, perfect, are going to tell us a bit about wearables, sort of in the spirit of the last series of lunch talks, so a bit earlier, given that we're ending earlier, thinking about new ways to collect data. And it's really exciting to have them here because I think this is, the data they're collecting is not specifically network data. I think you'll immediately see the relevance to the kind of work we've been talking about all week, and hopefully the potential to collect network data with these kinds of devices in the future. So that's the plan for today. It's a bit less packed than yesterday was. Congratulations to those who made it through yesterday. And there we go. All right, so I already said that. So this is effectively what we're going to do. And I'll just start. So this is a good thing to make up data. Simulations run a gamut from simple randomizations through to predictions. So you'll often use I find that simulations are a great way to help you. Let me brush back. I'm hyped up on hot caffeine and puppies from Mario. So what I mean by simulations are that you sit down at your computer and you write down a bit of code that implements a set of ideas about a social process that you have. Right? So literally it's the instantiation of your theory of the world in a machine. And so there's a bunch of tasks you have to do to get there. But then there's essentially that notion of writing down the world, a detailed version of what you think is happening, and then adding noise to it in a smart way. And so once you have that set up, what you've created is a very simplified version of the world that you can run experiments on. So this is why we do it after models and after experiments, because what you're going to do is essentially run experiments on us in a simulated world. So why do this? Oftentimes you do it because you don't have the data, right? So there are things you would like to know about the world that just don't exist, right? You can't go out and get the data you want at the level of the social mechanism you care about. So if I'm interested in social exchange and trust, for example, I have a bunch of surveys on how much people trust, but I don't have their day-to-day interactions to see how they behave when they actually are engaged in a market or trying to pick a friend or something. Oftentimes we're interested in unethical treatment effects. We would like to do things that you just couldn't do, either ethically or politically in the real world. So, for example, we know we can stop the spread of COVID if we would just lock everybody in their house. Or if we would make people stop having sex for about 6 months, we could get rid of the vast majority of HIV and STDs, certainly the bacterial ones, right? So we could do that sort of intellectually, but practically you could never do that, right? So it's an impossible thing to do and wouldn't be ethical even if you could do it, right? So there's all these things, but what's nice about these things is that if you can imagine what would happen if you did it, it helps give you a bound of what the range of the world looks like. So it helps you imagine what would occur in the world when you're trying to do something. So those are sort of the practical versions, and when you see the lack of data and ethical treatment sides, these tend to be simulations that are more tightly linked to the real empirical world. So there's an empirical case like disease diffusion that you care about. The other reason you do theory is or you do simulations is to extend theory. We often have theories about the way the world works, something that tells us what we think people do, and what a simulation is, right, beyond anything else, especially an agent-based simulation model like I'm going to talk about next, agent-based models are just your theory routinized. And the reason I say it's routinized is that anybody who spent any time in front of a machine coding things up knows that the computer does exactly what you tell it to do, right? You can't get it to do something, or you can get it to do a lot of things you don't want it to do, but it's doing exactly what you told it to do. And that's the advantage and the disadvantage. And so it lets you get at things that you might not understand from your theory just by writing it down. Particularly if you're the kind of person who can't look at an equation and say, oh yeah, that implies a peak over here and a double hump at the end or something like this. And so your ability to intuit log odds or differential equations isn't great, so maybe you can just simulate something and see what in fact happens when it happens. There's a lot of work to do for that side. The really nice thing for it is that it lets you see some of these emergent properties that come out of a system that's otherwise very simple. So if you have a process that people are engaged in, and that process is, at its, or at individual level pretty innocuous or pretty simple, you can ask how it scales when everybody does it. And so I refer to this as the Kantian moment of social science. Kant had this notion of ethics that I will my actions universal. That's what you get to do in the simulation. You can will the actions of your agents universal. And you can say if everyone behaved this way, or along the spectrum of ways, what would happen? And that's something again you can't see. The other thing that allows you to do, and this was so the disentangle otherwise conflated processes, is exactly with the knock-in experiments kind of idea that Carter was talking about yesterday. The reason these tend to matter is because most social processes that we care about, particularly in networks, have feedback processes and spillover effects. So whatever I do affects the agents next to me, and whatever they do then comes back on me. So you end up with this cyclic process of feedback, which is an inherent endogeneity, which gives the econometricians nightmares, but is actually the bread and butter of what we do, right? And so this is the way to actually get around that. You can also do a lot of stuff that are purely methodological. And so if you want to figure out, if your estimates are unbiased, or so there's a lot of simulations you'll do just to figure out if you're getting if a method you've invented gets the answer you want. So all of those things on community detection I showed you the other day are there. I think there's a lot of work you can do with sample design and construction to save yourself some time. So if you can figure out what kind of sample would I have to draw to get the coverage I want. There's a great property in networks called the network covering problem. If you want to figure out which set of nodes you have to sample in order to capture all the edges in the network. Well, you can simulate that on networks that look like yours and get a sense of what kind of sample you'd have to do to design, for example. All right. So I think that if you want to think about what you're going to do, you need to jump into this and really ask yourself, so why you're engaged in this process. And so I think Carter said it really nicely yesterday. It's like, what answer do you want to get out of this at the end of the day? What's the thing you want to be able to do? And so what you don't want to do is say, I want to simulate the world, right? So I want a map of the world at the scale of reality is not useful, right? You need a map of the world that is smaller than reality and more simplified so that you can draw, so you can see the big picture. And that's the same thing with simulation. And so you need to figure out what exactly it is you want to simulate. And is it going to be a guide to policy? Is it going to try to tell a practitioner that they should engage in practice X if something else happens? Or are you just trying to push the theory so you can figure out where that goes? There's a data versus theory version of this. So how much does the question depend on what's actually occurring in the empirical world, like in the range of things you see, versus what would occur in a wider range that's not improbable, right? Do you really care that cities have buildings that can't be moved and that only certain houses come for sale? Or do you want to think about the kind of results that emerge when people make choices without those constraints? And I think this sort of brings us to this realism question, which is, do you want to focus in on a single detail of something, or all of this sort of warts and bumps and bruises that have to do with the real setting you're dealing with? For those of you that have ever done an agent-based model or been in the room when people discuss agent-based models, what typically happens is you'll go in front of a group that you're sort of consulting with or what have you, and they'll say, I want to simulate income inequality in a city. And they say, okay, I can do that. Let's imagine people get jobs. Let's imagine they get fired from jobs. Let's imagine there's a distribution of skill, things like this. And they say, yes, but I also want to add neighborhoods, and I want to add gender, and I want to add dental coverage, and I want to know how old their kids are. And before you know it, you have this entire array of thousands and thousands of parameters, most of which probably don't matter, and most of which you don't have a theory for, but it's going to be really, really accurate. Lisa Keister, who's not able to make it here today, but she used to work for a simulation team called CoreSim. It was out of Cornell. It was simulating essentially age and income trajectories, age, income, and wealth trajectories for the Social Security Administration. And the level of detail that the Social Security Administration wanted was mind-blowing. And they actually wanted dental records built into the simulation because they figured that there might be crises that people have when they have to get crowns or something. And so it was like this level of detail can really get out of hand. So you need to think very carefully about what you do. So that sort of raises, I think, sort of the basic field of agent-based models. I put the entire world to me as a 2x2, so you can think of this as a space, right? And so you can have this realism prediction sort of axis versus an illustration and toy, and then you can have theory-based versus database, and then agent-based models will all fit in this space somewhere. So if you wanted a really realistic data-based simulation, you might do something like CoreSim, right? You might be trying to really figure out what the population distribution is today, what the birth rates are today, what their savings rates are, and then you push that forward, and you spend a huge amount of time in these kinds of simulations aligning your model. And so I want to make sure that the model for 1950 does a good job of predicting what happened in 1960 and 1970 and so forth, and you build in the kind of projections you need to make sure that each of these things are aligned with reality as best as you can, so that when you then go off to present out of sample, you're close to it. The real problem with this kind of model is all the work goes into that kind of alignment, and you're still never guaranteed out of sample prediction, and there's overfitting problems, and there's a defined art in doing this. At the other corner, you end up with purely theory-based illustration kind of models, and here you have things where you're just trying to learn something about a process. So I'll set up something that has nothing to do with reality per se. So I'll put people on a grid or on a circle or on a line, and I'll ask them to make choices about their neighbors. Well, they are just literally empty boxes that make choices. That's all they do. They don't have an age, they don't have, there's nothing else to them, but they do things. And then I can ask, what I'm really doing there is I'm asking a question about the result of this kind of choice action. And so there's a bunch of different sort of things in between, right? I think that a lot of the stuff that ends up being more illustration, but we really care about prediction, are things like traffic simulations, because you rarely put this on, the 405. Instead, you build a network of roads that has a certain pattern you care about that may not be real, but then you let the traffic do something that's real. So you have the intersection and you change the shape of the intersection. So that's, I just want you to keep that in the back of the mind, because I'm going to dig into some details. Most of my work sort of bridges really sort of down here. I spend a lot of time in the sort of more theory illustration side, a little bit up in this world, but even sort of my COVID work on this has been, the work we've done has been not trying to capture reality exactly. It's been more trying to illustrate a theoretical point. All right, so let's start then with some ideas about what you have to do if you want to set up one of these models. So I think that every agent-based model effectively has three parts. And so the first part is the environment. This is the thing, the setting where your agent acts. Right? And so this usually consists of a series of features that either constrain the action of your agents, or it provides resources that those agents get. And so that's the role that the environment plays. It provides a constraint on the things, a constraint on the resource base upon which agents can move. In our setting, that environment is often a network, right? It's often an underlying network of associations or friendships or sexual contacts or something, and that determines where things like disease spread or something. But there's lots of different versions of this, and so an n/8 grid on a Schelling model, and I'll show you an example of that in a second. And there's a space you can have. There's a classic model called Sugarscape where you just drop a little bit of bits on a landscape and these ants move around on it, right? And so you can think about that. The third part, is which people tend to get all the attention on, are the sort of these next two. I think that we underplay the importance of the environment. We'll come back to that in a bit. But the next set, of course, is you need, if you're going to have an agent-based model, you need to have agents. Agents are the critters in your model that do something, right? And so they buy a house, or they move, or they pass a disease, or they get old and die, right? So there's all kinds of things that your agents do. And the question is, you have to figure out what it is you want your agents to do and what's relevant for your agents to do, right? So if I'm doing a shelling and housing segregation model, I don't need my agents to exercise in the morning. That's irrelevant for that simulation. So just think about what it is that you think you need your agents to do, and really be careful about the kind of characteristics that they have. So effectively, whatever agents do, you're going to have to build a little holding object to carry those. You're going to have to erase or whatever you're looking for. Agents enact rules, and so there are rules at multiple levels. There are system level rules and agent rules. Agent rules govern how agents behave in the model. And the way these models work is that you have some kind of a temporal unfolding, and at each step an agent engages with their environment or their neighbors, and they do something based on a set of rules that you write. And this is where most of your theorizing probably comes. So you need to figure out what rule you have that guides what the agents do. And the classic example that's almost entirely rules, in the actual structure tends to be predetermined, is something like the prisoner's dilemma exchange. That started these, a whole branch of these, the Axelrod and such did. In these models, you have what rule do I play to cooperate or defect? Do I do tit for tat? I do what you do back to you. Do I play Queen's Gambit? I think is the name of it. Where as soon as you cross me, I damn you forever, right? So there's a bunch of different models that you can play, and you might say, well, which one wins, right? It might be that being a jerk right out of the gate is the best thing to do. Well, the experiment in those kinds of Axelrod models, we're really asking, there are different theories that we can encode as different rules, and if we put agents together in an environment where they're playing pairwise games with each other, what happens? Then you have a global processing rule. And there are two parts of the global processing rule. One is essentially how long do things happen, right? So essentially, do things occur? Do we do a one-shot exchange? Do we do an infinite exchange? Do the agents know how long the simulation is going to end? Things like this. And then there's a microprocessing rule. It's like, do all the agents exchange simultaneously? Like, are you trying to simulate actual parallel processing, or do people work sequentially? These can have important effects on the result that you're trying to get to, so you want to make sure that you can think through those as you go. So I'm going to start with the classic example of this. This is the down in that toy illustration corner. This is known as the Schelling segregation model. And in the Schelling segregation model, Schelling was an economist in the, I think he wrote this in the late 50s, early 60s, something like this. I should have a site up there, but I don't. And so in this case, what we have our agents are, I'm going to call them people. The negative people call them turtles. The agents are boxes. Right? These are voxels on the machine. And you can be either red or blue. That's what you can do. The environment is just a 50-50 grid. This is some kind of an analog to a city. That's the thinking here, that there's something about this space that we can think of, because we want to let our agents move from one part of the city to the next, depending on how happy they are. So in this case, it's a 50-50 grid. It's not actually a 50-50 grid. It's a 50-50 cell space, but it's a torus. So this side is linked to this side is linked to this side. And so if an agent moves, this agent's neighbors are these people around it, and those three up there. So it's all wrapped around this up, as Neil said. In this case, I've set up the environment to be pretty dense. You'll notice there's very few empty squares, right? And so that's an element that you might not think of in something like a model like this. But if I'm going to have a model that says that people have to move around, there needs to be a space for them to move to. So there has to be some empty space where the place locks up. I can't live with somebody else. So that's my rules. And so the rule set said if some proportion of your neighbors are the same color as you, then you move. If more than that percent are the same color as you stay. And so it's a very simple threshold model. And so the process says that the process that Schelling was trying to capture in a toy sense is this notion of people fleeing the inner city in the 60s or some other sort of feature to get people that are racially homogenous. So it might be that if I'm a white person, I want to have white neighbors. If I'm a black person, I want to have black neighbors. And so if I find that there are black people moving into my neighborhood, I run away. That's the kind of model they're saying. And so what he wants to say is, what kind of segregation at the city level are you going to see when people have different levels of tolerance for neighbors that are disliked them? And so in this case, we say that people want to have at least 70% of their neighbors like them, and that they're willing to have 30% of their neighbors that are different from them. And if that's the case, then they're happy. If not, they move. Notice it's not the amount of happiness; it's just binary. You're either happy or not. And moving is costless. So there's a bunch of things about this model that are not there. So you run this model, and what happens is you get a bunch of these completely homogeneous sets. And so despite the fact that people are willing to have neighbors that are different than them, in practice, what that very simple rule set leads to are these pure homogeneous tracks where people are all the same. Right? And so most of these people in this network or in this setting end up having neighbors that are 100% of them are just like themselves, even though they're willing to have 70% of the people that are like themselves. Right? They want to have at least 30% of people who are like themselves. Now, if I set up the exact same set of rules, but I leave more open spaces, what happens? So notice I've changed the environment in this case. I've just changed the number from 246 to 2009. From 21 to 24 agents. Keep the same set of rules, and what do we see? Right, you end up with roughly the same kind of set, maybe perhaps a slightly bigger set, but notice that people that have no neighbors around them are happy, because it's really a model that says, I want to have people that are like me, I want to not have people that are different from me next to me. And so that model then means that you end up with some sort of these big open sort of spaces. Ascending again, now I set it to a 50-50 threshold. You get bigger, denser sets, and so forth. And you can play a bunch of these games. And so what was the takeaway that Schelling and others have taken from this model is that people can be quite tolerant, right? They only want a little bit of in-group preference. And then the emergent property of this game is that you end up with highly system-level segregation, even though people are willing to have local-level integration. And so it suggests then that if you're going to, these kind of tipping points are nonlinear. That's the way these models are. All right. So there are other sort of elements you need to think about when you build these models. So one is you need to think about these update rules. And so do you update parallel versus serial? In this one, this classic Schelling model, each agent makes a decision one at a time. So you're moving through the state space of each agent at one time at discrete time ticks. And at each time tick, you randomly select a person, you have them look around and whether they're happy or not, and they move. The next time tick, you randomly select one person making a choice each time, and that creates and that's in some sense a necessity of this model, because other people move in parallel, otherwise two people try to move to the same spot, and you need a rule for who gets to win that spot, right? So it's much simpler to do it this way where you have people move at one at a time. If you do a parallel update, it means that there's the state of the system at the top of your iteration. Every agent goes through and makes their decision based on what's going on around them. They implement their decision, and then you update the environment for every agent. And so this is that everybody's acting simultaneously, as opposed to sequentially. And in many ways, that's reflective of the world we live in, right? In many settings, when I'm up here speaking, Carter's getting coffee, and those things happen at the same time. And I don't have to wait, he doesn't have to wait for me to stop speaking in order for him to get coffee, or vice versa. And so we can imagine that this kind of parallel feature works well in the setting. But you need to be careful, right? You need to figure out whether or not your setting works that way. If you're doing radio traffic in the World Trade Center, then it might actually make sense to have things work in real time and have the simulation work in discrete steps where only one agent can talk at a time, because radios otherwise talk over each other, right? So you can imagine it working like this. The kinds of differences that you get is that whenever your rule set depends crucially on agents reacting to the environment, sequential unfolding tends to create smoother outcomes, because effectively you have much tinier changes on the margin. What happens when everyone decides simultaneously is you get a lot, the models can take a lot longer to converge, and they can converge on somewhat weird spaces because people are constantly adjusting to go past each other, right? And so no one gets happy because they're all moving simultaneously, so you get lots and lots of them. In practice, these things are literally just where do you put the update in the for loop. So it's just as easy to do one as the other. If you have a really massive system where you're doing lots of changes on a big scale, then the parallel version actually allows you to parallelize in a way that you can't do if you're doing truly serial, but that's usually a trivial bet. The other update rule is, do you do a fixed or random update? So notice the way I described the Schelling model as implemented in the Negapi case there is that each agent is picked at random, right? That means that some agents might never get picked and other agents might get picked many, many times, right? Alternatively, what you can do is say, I'm going to go for each time step, go through each person and do X, right? And so then in that case, each person gets a sequential order. You can either do it in a fixed order from person number 1 to person number n, or a randomized order. Person, just randomly pick one or the other. I recommend doing randomized order. That sort of seems to me that the order of your nodes initially should not ever matter for anything we do. But I can probably be convinced that there's another reason to do it. If you're doing a serial update and you're always updating people in the same order, then that's a feature of your environment, right? So that's something that's part of your simulation that's baked into what you think the reality is. And maybe that's true, right? Maybe if you have a pecking order, the big gorilla always gets to eat first. And that's true every day, and that's a resource allocation feature, and that's something you add to the model, and that's perfectly reasonable. If you don't know that, then randomizing probably makes more sense. The other sort of feature of your environment that you have are these update rules. So what happens to your population? Do you have a population that turns over, or do you have the same set of nodes that's set? This is usually a generalizability kind of question. So what are you trying to infer to from your model? When I do disease simulation models of something like COVID, I'm willing to take the assumption that I'm dealing with a fixed population. Well, some people can die, but I'm not going to let new people into the population. I figure I don't need, for a disease that's going to run maybe 3 years, I don't need to get that kind of a level of realism in for the kinds of questions I want to ask. Now, if instead you really do care about the ways in which population turnover matter, if you're doing the kind of simulations that Ashton was talking about with kinship structures, then your population needs to update. When people die, other people need to get born, and it's part of the process. If you have an inheritance model where you're trying to figure out how inequality spreads through generations, then you need new people to enter the generations, and you need rules for updating those sets. And that can actually get quite complicated, right? So if you're trying to figure out birth and death rates of your agents, you need some rules for each of those steps. You need an allocation of people to partners and things like this. And so it quickly spirals into lots of things to do. Population, yes, that's what this node is. So just be careful that the distributions you get, one of the things that happens, classic sort of first-time error, you sit down and you write up your simulation and you have a really good model for how the age at which people have babies and so forth, but you started all of your population with 20-year-olds, and you start all your population with 20-year-olds, they all have babies at the same time, they all age at the same time, they all die at the same time, and your population does this, right, all the way down. You don't want that, right? So think carefully about where you enter the process, how you burn into the process, these kinds of things. All right. The big sort of nitpicky part of this of any agent-based modeling project is figuring out what the values of your parameters are and the number of parameters you need to have. Most simulations have a set of control parameters, things that guide the action, and they have some number of substantive parameters. And I'm just putting this up really to be I think, particularly for non-data-based simulations, you want as few parameters as you can reasonably get away with your theory. Right? The more parameters you add, all you're doing is creating complexity for yourself. Now, your system might require complexity. If it does, great. That's a feature, not a bug. But if you're just adding parameters because you think it might matter, and I have sort of this notion that in reality people have different ages, and so I'm going to add people at different ages to my model, even though I don't have a theory about how age does anything in my model, then that's probably a mistake. And again, this becomes more of a problem the more sort of you move along this realism line. People will push you to add parameters or variables that describe what people do or who they are. And I'll give you some examples of that in a second. The other sort of feature is we often don't have a natural scale on the value of parameters, right? So for something like a Schelling model, I have the proportion of my neighbors, so that's a reasonable, I can think about what that means. But oftentimes I want to say, I'm going to take the advice of my friends versus the advice of my parents. What scale is that on? All right, so you need some way to think very carefully about how you tune these parameters to be comparable to some decision you want to make. The final point, I think is the final point. No, of course it's not. You need to think about what it is you're simulating, and for networks in particular, we tend to have simulations on networks or simulations of networks, or as Sam's going to talk about, both. On networks tends to be the simplest of these two, right? And so what you end up doing is saying something is moving across the network, so diffusion or idea or beliefs or something. And so you spend all of your time with the rules. You can treat the network itself as fixed, and that's a huge win from an implementation standpoint. It's a lot easier to change the state of the actors than it is to rewire the state of the network many times. And so the efforts in these kinds of effects tend to be focusing on the agent rules. Now, you don't necessarily have a static network in this case. Like I can have a fixed dynamic network, or I can have a level of something that's changing, but it's not changing as part of the agent rules. It's a scheduled change or something I know that occurred in the past. Simulation of networks is a lot of the work that we talked about yesterday in terms of these sort of knock-in, knock-out experiments. What kind of structure do you get? But we can have, I like to think of largely these two sorts, right? So you have exogenous networks where you build the network based on some kind of feature, and then maybe that feature changes, like a belief structure or political beliefs, and then people rewire their networks. And so that ends up starting exogenous, we have some characteristics to go through, and then it works in on itself as something changes in the network. And you can do this, so that now one of the nice things about both Ergom's and Siena models is you can simulate networks from rule sets based on those, and that's a nice way to generate a family of networks. But you might have something more exchange-based or something, where your theory is about how people change networks. So I just want to be, so those can often be times where you just write those rules yourself. And a classic example is social balance. If you think of the friend of a friend as a friend, my enemy's enemy is my friend models that Craig was talking about on day 2, like those models can be put into sequences in real simulations. You can put a bunch of people in the network, you can see different kinds of distributions of friends and enemies, and you can say, let's play the rules and see what happens. And it turns out that it's not as always easy to get to the final equilibrium solution as you think it might be, because people move past each other. And so you can learn some things from those models quite nicely. Often, so if you're doing both, then you want to make sure that you have the, again, just make sure that your rules are guiding. All right, some perhaps non-obvious cautionary points that I want to throw out there. These are another sort of title for this slide would be mistakes I made that you don't need to make when you're writing. Is make sure you have some, whenever you're doing network simulations, things can build on themselves in really ways that you might not have built into your simulation to start with. And so if you're not careful what you're doing, you can do some pretty silly things. So degree constraints, for example. So does the setting you're modeling come with any activity strengths? It probably does if it's a social network. People only have so much time in the world. But if you have a model that says a friend of a friend should be a friend, it's really easy for that model to say you should be friends with everyone. And so ask yourself if that's what you want. And if it is what you want, great. If it's not what you want, ask yourself how you want people to trim their friends. Do you want them to, like, is it a replacement model? Is it a time to spend together model? Or something like that. Right? So one quick solution, of course, you can just fix degree and focus on changing the other side. That's a pretty heavy-handed one, as we talked about yesterday. But it might be the best solution if there's something else that you really care about doing. I think a lot of times in the simulation world, we don't think much about agent memory. We tend to, as human critters, we live in a world that's rich with meaning, and we all have memories that are more or less accurate of the things we've done in the past. But in simulation land, we tend to just have a Markov chain. So whatever the state is at time t, that affects the network at time t+1, and everything that happened at t-20 just doesn't matter anymore. So imagine a Schelling model, right? What the Schelling model does is people are just jostling around, they're moving the space, and I'm happy to move back into a house that I moved out of. Most of us in the real world would never do that. Once I live in a house, it's dead to me. I don't go back there, right? Because whoever I sold it to screwed it up, and so I don't ever want to see it again. And so, maybe that would matter for the model, maybe it doesn't, right? And so you want to think for yourself whether or not your agents have memory and whether that applies. The reason that most of our simulations don't have memory is that it's expensive to carry that memory, right? Because if you have a series of interactions with other people, you need a structure to store that a series of interactions, and you need a sequence that goes with that. A nice sort of simplifying solution is to sum things with some kind of a moving window, right? So you can make it possible that I remember the last k iterations of things that I've done, or the sum of those iterations, or the result of those kinds of features. But just make it clear. This came up when people on some of this work we did on romantic relations. It's if you break up a romantic relation, you're very unlikely to go back to that relation. It's not that it never happens in the real world, but the reason that people inherit friends in the divorce is that those people don't want to deal with each other anymore. And so this notion that a breakup is a one-way street is a constraint. It's a memory constraint on the edge. And so you want to think carefully about how that's built in. It's also possible to get runaway configurations, so feedback processes and models that can easily walk into spaces of the world that are just truly what you didn't understand or intend. That's usually informative. Like that's usually actually a signal, not noise. And so it says you programmed something in your theory that you thought you operationalized right, that either you operationalized right and meant something entirely different than you thought it did, or you didn't program what you thought you were programming. And so spend some time very careful. What this really says is these runaway configuration models is to really, the idea is that when you could have something occur that you really want to make sure that what you're doing is realistic within the bounds of your theory. The classic example of this is that there's a reason that the peer influence model, the rows of the W matrix sum to 1. They sum to 1 because then the idea space never gets out of the bounds of the original distribution of the range of the ideas that were there. If I allow my friends to not just average their ties, but add to their ties, then all of a sudden my Y values in that peer influence model can sort of go off into crazy parts of the space. And so I can end up having people driven to high extremes. Now maybe that's true, right? Maybe it's the case that a co-rumination and a bitching about politics kind of model actually has this amplification effect. If so, great. And to what extent? What's the range? What does that mean? You gotta think about it. And just be clear that you're thinking about it. So in prior years, I've gone through some detailed examples of these are just a list of those. If you go onto the DNAC website, you can pull up the prior slides and you'll see some of these features. What I wanted to do now is talk about a couple of different models that we're currently working on, just to give you some under the hood ideas about sort of the ways that some of these things might be implemented. Before I go into that, and then after doing that, I'll give you some implementation ideas and software sort of suggestions. Does that seem to work? All right. So let's talk about one of my favorite examples, which is complex contagion. So Damon Santola and Macy have this model that says for social goods moving through a network, it's not sufficient to treat it like a disease that one infected person kind of comes in contact with one susceptible person, but instead, as active agents thinking about adopting something, I look around my network and I see if multiple people are using it, I'll adopt it. If multiple people are not using it, I won't adopt it. And it turns out that can have some really interesting implications on the spread of things through the network. And so if you imagine what that looks like, if at time 1, this pair of people are connected, at time 2, this one person could adopt. Note that at time 2, this person couldn't adopt. And that's because you need at least 2 of your neighbors, and only 1 of their neighbors has adopted at this time. And so you end up having this tiling effect that the only way that things can spread through the network is that there's at least 2 edges on the network that it can go, at least initially, to get started off. Now, if one tile went this way and one tile went this way, it's possible that you get bridges across, but it requires in its initial spot to get this kind of tiling process to go. So we can ask, like, well, what does that actually imply on a set of observed relations if that's our rule? So, and it's a very simple simulation. You seed the population with pairs of adopters who know what they're doing, and at each time step, their neighbors get the opportunity to adopt or not. And in this case, the decision was purely at the maximum. So if this is true, then I adopt. There's no coin flip or anything. It's a very simple walkthrough of the space. And we randomly picked 2 ties to start in order to get this initial condition so that someone could have 2 ties to start from. Now, you could randomly start from anywhere with 2 pairs of the neighbors or multiple pairs. But we figured this would be a nice, easy way to start. So we start like this, and what happens, we find that the vast majority of the time when you run this simulation, the thing dies out, right? So the proportion of people adopting the mode is just a couple more people than the ones you start with, right? And so the few people come in and say, look, we got these great new devices, come and use it with us, and no one else does, right? So it dies out. But if it makes it past a certain level, then many people adopt, right? So it has this kind of nice bimodal distribution where you end up with either no one adopting or everyone adopting. And it's because of this threshold effect. Now in reality, you're going to end up, this everyone adopting is the absolute best scenario, right? Because it says that if two of my alters adopt, I then adopt. Not if two of my alters adopt, I have a probability of adopting. Like this is really a high-end outcome. The setting matters for this outcome. So it turns out that the strongest parameter in the model that governs whether or not the size of the ultimate number of people who adopt is the local transitivity ratio. And that's because that initial takeoff requires tiling in the adoption process. But the global structural cohesion, the number of independent paths in the network, conditions the effect of transitivity. So this is a nice emergent feature. And so this kind of pattern you don't see necessarily in something like disease diffusion, because in disease diffusion it's easy to pass over these bridges, or it's easier to pass over these bridges. The other kind of an example of a simulation on a network is, oh please, go ahead.
Asking about the K, if I don't know going into it how many peers I need to have adopted for me to adopt, or I've already listed my data for you to have out, or what if you don't know that?
Yeah, so the question was, if you don't know what the K on the Centola model is, what number do you pick? And the answer is you have to just guess. You don't know. And so you can guess empirically, so some of the work that Tom has done and others on adoption and diffusion. What we used to call adoption thresholds are actually a function of the number of your peers who adopted prior to you. And so you could use you can use his tools to estimate those kinds of models. But for a simulation feature like this, notice that K2 is the lowest possible K you could have, right? So it's the case that I'm ending up with just one more person than simple contagion. And even with just one more person than simple contagion, you end up with much lower threshold. And so again, this is why I refer to this as a toy model, because I just wanted to learn essentially what effect that would have and how it was conditioned by the network. If I wanted to try to sell to a company how to get their device out there, I would need many more parameters to figure out sort of those kinds of issues, like how sensitive the population is and such. I had this idea a few years back that many of the problems with things like this adoption or other sort of adoption of innovation stuff, they tend to be binary adoption features. So the idea is it's like a cell phone adoption or Betamax or something like this. It's a purchase. You buy it, you have it, you've adopted it. And then you try to convince other people you're cool and get them to adopt it too, so you don't look like a weirdo. But many of the things we care about in the world, particularly are mental models. And I think most mental models need to be reinforced. They need to be nurtured temporally in order to be sustained. And the classic example of this is something like a second language. If you learned a second language at one point, as long as you're practicing it and keep doing it, you can keep speaking that second language. But you go a few years and you don't speak it, and it's gone, right? And so you need to reinforce it for a while. And so I said, I think you can conceptualize this as a diffusion model with forgetting. That I convince someone of what's happening, and then once I do, it decays over time. So I think, hey, this is great. Social networks and health are the best thing in the world. I can't wait to keep doing this. You go away for a week, you get distracted by someone else, something else happens and you forget about it and it sort of falls down. So let's imagine we have a process like this, right? And so we have a population of actors who are linked by network ties, and I use real networks, just observed networks. I don't think I was using Prosper or Health, I don't recall which. And so these agents represent people, and the rules are agents adopt a belief from their neighbors stochastically. So if I'm connected to someone who holds a belief, there's some probability that I do it. It ends up, just if you want to know, it's a random binomial draw based on the number of my neighbors that have the belief. And in each T, the salience of these beliefs drops by some constant feature. So it's a very simple, and then once a belief goes below a threshold, you can't do it over again. And so the general rules are, actually, you adopt a belief. It's not just it's the proportionate to the weight is proportionate to the amount of belief in your local ego network. And so it takes if you're surrounded by a bunch of neighbors who weakly believe something, you're unlikely to talk about that, which is the logic. So I'm using sequential spread, and I ran in a randomized order and a stopping rule implicit on the state. That is, when the disease or the idea is either held at a steady state or goes away, I stop, or after some number of iterations, I get tired and stop. And so this is what it kind of looks like. I took these three, in this case, this is an example of where the set went. You can have I characterize these networks by the amount of average pairwise connectivity. So this is Moody's favorite cohesion score. And so really cohesive networks and less cohesive networks. We engage in this process and we ask, well, what's driving these different features? And under one set of parameters and one set of bits, you can see that there's a really strong conditioning effect of the number of independent cycles in the network. And so it's the case that in order to sustain a belief, you have to have these lots of little loops, right? Or you don't have to, you can get one out here, but you're more likely to get a good sustained belief system in the entire setting if there are lots of different loops for people to talk about. And it's because you have a conversation about certain networks health with one person and then later with another and later with another. Another example, this is social exchange with homophily. As many of us, we've been thinking a lot in our department about, we've done a lot of talks and a lot of discussion of structural racism in our department. Not in our department, but in the world that our department is talking about. And as a quantitatively inclined sociologist, a lot of this work is pretty frustrating because it tends to be very hand-wavy, not really tied to anything with what's meant by structure. Is it structure of the mind? Is it structure of the setting? Is it structure of history? Like what is actually there? What's the measure of it? It can be really gross measures at the state level that are always endogenous. And so we're thinking, is there something about this that a network person can think about this structure that is fundamentally different than those models? And one idea is to build off network exchange theory. And a very simple model of network exchange theory comes out of Reitin and Morgan. And Reitin and Morgan had this idea that networks imply very different contact rates by group size. And so group size has a nonlinear effect on the extent to which something can flow through the network. And so I said, well, what would happen if we applied a Reitin and Morgan kind of model to a trust exchange game? And we said that people are engaged in the community, they're out there doing things with each other, and when they do things with each other, they're implicitly engaged in a trust and an exchange process. So if I trust you more, I'm more likely to have a successful interaction. If I trust you less, I'm going to have a less successful interaction. And so we can implement this model. It's really, this is the world's simplest game theory model. It's just a coin flip, right? So there's really no strategy here. It just says, when my finger gets burned, I take it off the thing. That's all this model says. And so, but I put that model in a series of different kinds of environments and ask, what does it imply? And this is, if this sounds familiar, this is exactly what Martina Morris and Jimmy Adams and I did with HIV exchange, HIV spread by race groups. Your HIV is higher in minority populations than it is in majority populations, and one explanation for that is that minority people are degenerates and they do all kinds of things that they shouldn't do, and if they would just behave themselves, it would be different. But it turns out that if you just look at the exchange patterns and treat everyone's to having the exact same set of patterns, you still get massive inequalities and higher HIV and STD rates amongst minority populations because their mixing part patterns are constrained. And the pool they're moving in creates greater numbers of loops at higher levels of natural concurrency, which then creates greater opportunity for disease. So you don't have to assume differences in people's propensities or behaviors to be, more or less promiscuous in order to get different levels of disease spread. And so the thing is, can you apply that model to something like a general social exchange? In order to do so, we imagine that people have a very simple sort of reward structure. So there's a baseline sort of level to how much you trust the person from the other category that you're interacting with. So I've had a lot of experience that's been positive, I will trust them more. I've had experience that has been bad, and I trust them less. So this is a learning model. So each agent has this propensity that says, I start out at some baseline level of trust, where it's in this case, as the example, it's a coin flip. And so if I flip that coin and I lose, I trust that person less, that kind of person less. If I flip that coin and win, I trust that kind of person more. A very simple model. We can then add to that a couple of different sort of ideas. I couldn't help myself. I should have stopped there if I had followed my advice for having one single parameter, but let's not. But I couldn't do it. And so let's assume then that we break our population into in-groups and out-groups. Right? And so what we have is an out-group bias. And so if they're in my group, right, so the zero, a person of type 0 exchanged with a 0, a 1 with a 1, you have this upper curve. If you trust other people from the out group a little less. And so the difference in the way to extent you trust them is this little out group bias gap. So that's some parameter that you can set, which is the out group bias, and that parameter, you could set it for each different combination of groups. You're going to see that I keep it the same for pairs just for comparability. And then we also say that if there's really a learning model, then you don't keep this schedule set. At some point you get enough experience that the difference in the kind of person goes away. And so I have my initial sort of preference that happens this, but after enough experience with that person, it goes away and everybody treats the same. You don't need to do this. This is actually a conservative assumption in the model. If you keep the bias all the way through, it just exaggerates the results. So let's imagine a world, right, where you have two equal-sized populations and everybody behaves exactly the same. You flip this coin. What you get are a bunch of random walks through the wind space. Some people flip a lot of negative coins. They then trust less, and so the bias is to flip less and flip more negatively. And sort of these are the curmudgeons that live in cabins in the woods by themselves and send out letter bombs. Or you end up over here and you flip a coin. You keep flipping a coin at 1, at 1, at 1, and all of a sudden out here you think yourself more Cuban and you sort of won the world. Everything's good. You're a great entrepreneur. It's all random walk. This is just coin flipping, right? But it's coin flipping with luck. And you'll notice something, of course, here that in this case, this is our baseline. Everybody's effectively exactly the same, and there's really no difference. In this particular case, the cumulative level, if you were to take all the people and add up the number of coins they've accumulated that were heads, you'll see that they end up having a nice positive growth. And that's because the system starts out with a greater than 50-50 chance. And so it's a positively biased random walk, and the parameters say that everything is, you trust people eventually if you win often enough. And so on average, most people do well, some people do better than others. You're always going to get inequality out of these models, but there we go. Which is a different lesson sociologists should learn, but that's a rant for another time. All right, now let's assume that we have outgroup bias. Right? We still have equal-sized groups, but we have an outgroup bias. So I trust my group better than I trust others. There's some bias that I add to these models. And in the in-group zeros, in-group ones, cross groups, you see this kind of a pattern. You see the same exact pattern we have from the last slide moving here, where the random walk is positive, but the cross-group ties are negative. So the more cross-group ties you have, the more likely you are to fall. But because these are randomly sized groups, and they're equally sized groups, which means that on average, people do the same, notice the inequality has gotten larger, right? And so we've added more chances to lose in this model. And so the inequality overall goes well. One person got really unlucky, right? So this is an outlier case. There's a whole sort of story about rare events, and that was an interesting rare sequence. It was driven by this really initial series of bad luck. So now let's imagine then, so the personal accumulation is effectively the same. That variance is trivial. Now we're going to try a different kind of model. What we're going to do here is we're going to say we have the exact same set of parameters, right? But we've just now shifted the size of the groups. And so now we have a majority and a minority, and we have majority to minority ties and minority to majority ties. And you'll notice, right, that these things are different sizes. But the curves are exactly the same. There's no bias at all. You get positive, it's a positive random walk, because that's where we start, and you end up seeing that kind of a set. Right? And you get a nice positive accumulation. Now we do the exact same thing, and this time we do it where the outgroup bias is exactly the same. So majorities distrust minorities at exactly the same level as minorities distrust majorities. So I don't have to assume any kind of asymmetry or behavior or what have you, and everybody trusts themselves exactly the same. So every person at the individual level acts exactly the same as every other person at the individual level. The only thing that's different here is the difference in group size. You play the game and you look at the pairwise exchange histories, and you can see that they look, how would you'd expect given those two numbers. And so you see what that looks like. When you sum up within groups, you get a radical different outcome. You see that the majority wins most of the time and the minority loses most of the time. And that's because for each individual portion of their within or cross-group ties is structured by their opportunity to exchange within or cross-race. So in this case, you see that minorities, the vast majority of their ties end up being with white people in this case, if you're black, whereas white people, they have only a minority of their ties with blacks. And so even though the trust levels and thus the expected return within cell are different, the fact that there are so many more of these ties for minorities than there are for majorities means that minorities lose. And this is I think this is a good example of what a real structural racism picture might look like. And we would see this in healthcare. Like if we find that if you're a patient and a doctor, you have these kinds of distribution of set, your trust in the health system, if there's just a little bit of distrust, it magnifies more for the in-group than the out-group. And so this is just box plots of where that goes. There's all kinds of different ways you can play this game. There's all types of ways that you can imagine what you have to do to fix it. And so if you were to imagine sort of the buy black movement, to say buy within your community, as you add some positive coefficient to the within group cell, say, well, you got to pull yourself up by the bootstraps, that coefficient has to be pretty big to make up for this difference. But it ends up having this kind of a model, that the curve you have for in-group and out-group ends up looking different depending on which set you are. But you can play that game and you can do it in lots of different ways. And there are ways then, what that ends up doing is it means the within group ties have to be really, really positive. I notice there are no orange lines coming out of here. So we have to have a really biased in-group set in order to make sure that we can counteract that sort of preponderance of off-group ties. So that's just a one way of doing that. What's fun is Kieran Lelly, the guy who did the Shiny app for our IdeaNet software that you saw the first day, did the same kind of thing with this model, mapping it to the racial distribution of each state using our Shiny and our census. And so you can actually pick out for any given state and any given race combination a set of assumptions about how much they trust the in-group and out-group, and you can see what the differential return in that place might be. Right? So I think this would be one way of operationalizing that set. And I'm already now at the end of where I'm supposed to be. I have a whole other thing here on disease spread that I didn't get time to get to, which is too bad because it's kind of fun, but I won't talk about that now. In the slides, you'll see a set of parameters or a set of guidance for software that you can get. If you're just getting started in this world and want to play with something, NetLogo is great. It's a great place to learn these toys, and the coding language is really easy. It's really easy to get under the hood, and the beauty is there's this whole sort of array of models they have that you can just modify, which is nice, and so it's there. My complaint with NetLogo has always been it's just a toy. It's sort of you can play with it on your machine. But now there is an NetLogo package that allows you to sort of wrap a toy into a wider set of experiments so you can then collect the results up and do things nicely. And that makes it a much more research-oriented tool than it used to be. All right, a couple of other different bits I'll skip just in the interest of not stealing too much of Sam's time because his work is actually more important. But yeah, so I'm going to stop there. My apologies for both. Questions, comments, thoughts? Please. The question is there a handbook to go to of some sort to guide this work? There have been a bunch of them. And I think that, as Carter alluded to a couple days ago, there was a big spate of these that came out in the late 90s, early 2000s, driven by Michael Macy and a few others in the social sciences. And there's a couple of great annual review of sociology papers, for example, that have sort of picked up on simulations and agent-based models. I'm sure there must be a handbook of agent-based models. I haven't looked for it. The old sort of the equivalent of Wasserman and Faust in the agent-based world is Simulating Artificial Societies is the title of the book. And that's a great example of going through these features. I'm just drawing a blank on his name. You remember? I'll send it to the list. What's that? Not the, that's another good one. Yeah, Joshua Epstein. Yeah.
There were I can't remember the names of the authors. There were the old silver books.
Yeah.
There were fairly general textbooks on simulations, social applications. Again, same era, 90s era stuff.
I think the field of this work has sort of bifurcated in a couple of different directions. There's still those of us that play with the toy models to learn insights about social processes. And then there's the consultant group that have been funded largely by DoD, some by the big money sort of bank world, and they're doing really detailed, essentially war game simulations. And those models, the place to do there is to find somebody at RTI or the Biocomplexity Institute at Virginia to essentially talk with you, and they have those kind of stuff. All right, thank you guys. Oh, please, one more question.
So can you use this simulation model to point in a pilot train?
Yes, I think that's a great reason to do these kinds of models, is you simulate something to say, this is what I would expect to happen when I go collect real data and test it. Pardon?
Yeah, I think another way, there's lots of different philosophy that alluded to, my talk, there's been a lot of very back and forth between the debating how to do these things, and sometimes someone will this way. But another way you can get at the same kinds of things you're talking about, that I have to say I often think in the end is more productive, although not always, with these other models that have been insightful, is start with a more realistic model, like a more realistic program or a SAM, something that people actually can data, but strip the parts away. So strip it down to its most elemental parts, so a two-way version of an approximation to a real model. One advantage of doing that is, you know what it is, right? Because it's the same kind of model that you use, but it's just a very simplified approximation. Another nice thing is that if you had, even if you don't intend to integrate it, you could fit it to data, you could use it as an approximation. It is approximating a realistic thing. So if you have a model that's from the design, a simplified approximation, a spherical cow, a real system, but there is a cow and you could, approximate it by a sphere. I think it allows you to make more contact with actual empirical models, right? So it increases your ability to deal with these complexity issues, to deal with calibration issues, and to be sure that what you're getting at the end of the day can be related to something out there in the world. And yet, you retain a lot of the ability to get insights from a simple system. I think that is often a more pragmatic way to go. Not always, there are good reasons. The Schelling model is famous for a reason, but that can be another way to get started. And then in terms of how to do it, right, you already have all the tools you need, just sort of stripping things away. That can be another way to go.
That's a good idea. That's one of the reasons, just intuitively, I always start simulating on real networks. That has a simulation on an Ergos random graph tends to be that informative. All right, happy to chat about this over beer.